other studies were in communication system engineering, and then I went to this program, the ICMC, and I did my PhD with Udi Zohari here, and then I moved to London to work with Masoud Hussain. He's a neurologist, cognitive neurologist. Some of the data that I'm going to show you here is from this period. And then I came back here to psychology department in something less than 2 years ago. Okay, so that's the story. And the topic that I studied since the beginning of my postdoc is visual working memory. Okay, so I will do this talk. I will start with introduction about a really big debate in the field of visual working memory, both in neuroscience and in cognitive psychology. And then I will move to a little bit more to my data to see how it relates to this big debate. Okay? Works? Yes. So I will move along. Okay, so what is visual working memory? There are many definitions about what visual working memory. One of the good definitions, I think, relatively good, temporary retention of information no longer present in the environment, to its manipulation and to its use in guiding behavior. Okay? And the basic question about working memory, and especially visual working memory in my case, is about the mechanism underlying working memory. As I see, in order to understand such very abstract concepts, we need to talk more about the mechanism, especially neural mechanism, but also cognitive mechanism. And in my talk, I will concentrate on trying to understand what's happening when we forget information. Okay, we just saw information, and with time we tend to forget this information. And I will try to see how the findings that relate to how we forget information, what can we learn from that about the actual mechanism. Okay? So let's start with the paradigms, and then we will touch a little bit the debate over the concepts. Most paradigms in visual working memory use this kind of task. But first, participants just look at the center, then there are a few patches with different colors. A few patches are presented, and then when these patches disappear, and there is this delay around 1 second, and after this delay, another set of stimuli appears, and the subjects are required to say if this is indeed the same display as was presented before, or if it is different one. Okay? And what we as experiments, like in the experiment, we can play with the number of objects that are presented, and again, subjects are required to maintain this information, the first display, across the delay, and to compare it to the second display. So that's the traditional way people have been studying visual working memory, and the classic results are like that. Here in x-axis, that's the number of items that was presented here. Y-axis is percent correct, how many times, what's the fraction of times that you were correct. And what we can see is that when 1 and 2 and 3 items are presented, subjects have very good performance, and this performance degrades with the number of items in memory. Yeah.
You change only one square?
Yes, typically only one square. And change, and in this sense, the changes are pretty big. my approach, and my approach has, I think, better ways to distinguish like real memory processes than perception processes. But in that sense, here in in this case, it's really hard to take apart. If the problem, it might be just not enough time to perceive all the objects, and it doesn't really have to be memory. What people have done, they played with the amount of time that of the display, and they show that it's not really related to amount of time here. So you can that's strengthen a claim that it might be a memory process, but you're totally correct. Just only from this design you cannot really tell. But I think that's really important question. If you try to study, you say that you study working memory, to be sure that you can separate it from like visual perception or even motor stuff or just the comparison process. All the effects might be also related to the comparison process here. It's much more complicated, but that's just the strawman that I want to study.
Is there a reason why we call it visual working memory? I mean, the claim is that there's something special about this particular piece of memory as harnessed for the visual modality?
Yes, yes, there is a claim that it might be, and it's probably different processes than maybe verbal working memory, and there are ways to try again to separate like verbal working memory from verbal working memory. That's the more traditional way of like showing words or just letters, and then subjects are more usually use what people call phonological loop and somehow rehearse the rehearse the verbal tags. In this case, what people try to show that even here, if you ask participants just to rehearse like some kind of verbal tagging across the experiment, it doesn't really hamper the results here. So people and in imaging studies, you can see that in this kind of task, in visual tasks, people there is more recruitment of more visual brain regions. So people usually, I study visual working memory because I understand about vision, and that's at least my domain or my niche. I do think that some of the processes are really different, and I might talk to that afterwards, because some of the effects that I find, I think that it's really hard to find in more verbal domains because of this rehearsal. Here, it's in my task it's a bit harder to rehearse the stimuli, this verbally rehearse. So, okay, so that's the traditional way people have been using, and 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 in this task, it's really hard to because the change for really like category change from purple to yellow, it's really hard to say something about the quality of the representation, the quality of the memory representation that we have here, and it's all like what people have people use this data to say, well, we had played, we can remember up to 3 or 4 items fairly perfect, and then performance starts to deteriorate. But the reason that we might see like the same kind of performance for 1, 2, and 3 items, it might be just because of ceiling effect. People can't be better than 100%. And one, again, of the cons of this task is that that we have like only 2 possible choices. It's either they spotted the change or not. If we try to quantify it in the amount of information that we get per trial, it's just 1 bit of information per trial. So stuff, the nature paper really claimed that what we have some kind of it's called the slot model. We have items are just represented in slots in our mind, and we have around 3 or 4 slots, and when we try to remember more items than the number of slots that we have in our mind or brain, then performance starts to deteriorate. Okay, that's what they suggested in nature, and people still believe in this slot model. But in recent years, the paradigm has changed. The paradigm that people start probing working memory change a little bit, and also the conclusions or the theory about what's the mechanism underlying working memory also change. So let's look at the other paradigm that I'll put all the data afterwards that I'm going to show you. Going to use this kind of paradigm. People now call it the production task, delayed production task, or continuously forecast. And let's see how it works. So it's the first study that used this kind of stuff 10 years ago, but really in the last 6 years, more and more people use this kind of paradigm. Now, participants are presented again with different number of items. Let's say here colors, and then there is a delay around 1 second, and after the delay, there is a color wheel presented, and one, and there is a probe that tells the participant just to click on the color that they remember this item to be. Okay? So they see the different number of items. Here is a delay. They need to remember all these items, but now instead of just saying change or not, they just need to reproduce the color of a specific item. Okay. And now let's see what this fairly simple change from the different paradigm, what it can reveal us about the mechanism or the underlying representation that we might have in our mind. So first, one of the changes before we had just binary response, just change or not, one bit of information. Here, the space or the report space is much bigger. It's more analog response. We have much more information per trial, and we can also talk about the quality of the representation. Let's see what we find here. That's just a plot, like a histogram of the number of trials, the frequency of trials, with different error, right? Here, 0 error, it means the subject reported exactly the same color that was presented before. And 90 degrees error, it means the subject did very good. The green color was presented, and they reported blue, something like a very big error. So we have like more analog measure of error, and here we can see the frequency of this distribution, and that is here we can see plot when n equals 1. N is the number of items here. So when there was one item presented, participants were fairly precise in responding to the in reporting the exact color, and when there were 2 items presented, participants were less precise, and 4 even less, and 6 even less. So here we have some measure, a better measure of the quality of the representation. First, we see a difference between 1, 2, and 3, and 4. In the previous paradigm, there was ceiling effect. We couldn't see that, and we can see, and we can talk about the quality of the precision of memory representation.
I think I missed something. So when you say n equals 1, it's you're being requested to report one color, or
No, all the time you are just requested to report one color. All the time it's just about reporting one color.
N equals to 1 means that
The number of items that was presented, the number of items that you had to maintain in memory.
So there was one item 0?
so well behaved.
Yeah, so these are actually experimental data.
Yeah. Yeah.
Wow. How many subjects were there?
Huh?
How many subjects were there?
Subjects come, but I think that here there weren't a lot of subjects, but it comes for a few times. I was doing this test for a few hours in order to get more and more data. I think that's in science paper. And but it's and the red is just a fit of just fitting like a circular Gaussian to the data. But usually we also get like our data is maybe not as nice as here, but it's not far away from that.
Yeah, I have another question. The difference between these two tests is not only the continuous choice of colors that was described by Anton, it's also that the first one was a recognition test and this is a recall test, right? So it also may affect the way the results behave.
Yeah. It's my different types or kinds of probing memory, right? But I just want here to emphasize that the the benefits of using this. But in the other task we have much more information. We couldn't see really differences between one and two items, and that's why people suggested this slot model that you can have one item, you can put it in a slot. But this data supports more a kind of more flexible kind of type of memory, more here we call it the resource model, that you have one pool of memory resources, and this pool just is distributed between the number of items that you try to remember. It's not a digital type of memory of all or none. You have different precision, and the precision relates to the amount of memory resources that could be attributed to the different items. But again, yeah, it's a completely different task, but I think that's a good example of how changing paradigms in how you probe memory can change what your like the perspective about the mechanism underlying the process. It's pretty convincing. No one can really say, well, one item, you remember one item as well as two items as the slot model would predict, because the slot model is you have one slot per item. And so it's really like this science paper, highly cited paper that came from the lab that I was part of it in London, really changed how people think about walking.
It's unclear to me of the shape of this distribution and the nature of this analog signal that you're getting. If it really tells me anything about memory. Because it seems to me if you don't remember which color block was in that particular position, then you don't remember. It doesn't. In other words, like it's not more likely that you're going to think if the block was actually yellow, it's not more likely that you're going to think it's green or that it was red if you don't remember what the picture was. I think that the reason why you have these errors distributed between -45 and 45 degrees is either because motor or error, or because the first time you showed it you didn't quite get exactly what the color was. But if you see what I'm saying, if you don't remember, then you don't remember. It shouldn't be distributed around the wheel.
Yeah, but random mistakes would be averaged over.
Yeah. So your intuition, what you say is according to your intuition. If you don't remember, you just don't remember. Your intuition is similar to their intuition, to the slot model. And I agree. And let's wait. Only from this data, what you can say, well, here we have some random errors. In this case, this very big error, when you have 6 items, it might be related not to the crisp precision of memory, it might be just people randomly selected any color because they forgot. Let's wait with that because I'm going to show you data that really tries to distinguish these two processes and also to distinguish a perception and really memory processes. So I think that's a valid concern that you have, but I think that I will be able to show you that, and I hope to convince you that your really change how most, at least psychologists, think of memories because this data is convincing. About comparing like this mass or random errors or uniform distribution, what we can call, we're gonna see next. Next, we're going to see how we try to quantify it, and about the actual distribution that should be used to fit. Here we see that it's a Gaussian. It's called it's kind of Gaussian in a circular way, right? We have a circular here, and here it seems that the distribution seems to fit, but in future research, one of the papers that I sent you, people start talking about is it the best distribution that we can see. But it's just beginning, right? And now if we can just take the standard deviation or our measure of precision might be 1 over standard deviation, we can see a power law change in that, and nothing really, here the claim is that nothing really special happening after 3 or 4 objects. So, so here, like Bayes and Hussein argue that, well, what we have here is more appropriate to it's more appropriate to talk about some kind of a pool of resources that is just distributed around among all items that determines how precise people remember that, and it's less all or none representation or binary representation. Okay, so let's well, one of the things that disturbed me about like this study, that it's really hard to distinguish between perceptual motor processes and really memory. And my approach was to use variable delay. And I try to convince you what's the benefit of using variable delay. So let's see the task that I use. Here, I use only one item in different color. Then I use variable delay. It's randomly interleaved in the trial. Participants haven't had a clue of what's going to be the delay that they will have to maintain data. And then they need to report that out of the color what was the exact color. Okay? So now the benefit using variable delay, that now let's say the delay of 1 second, it quantifies all perceptual perceptual noise, motor noise, and memory noise. But if now I compare what's happening between 1 item and 3 or a longer delay, also in the 5-second delay we have the same perceptual noise, the same maybe encoding noise, and probably the same motor noise at the end. So if the comparison of the different delays is a better way to target what's really happening in maintenance in memory, and that's a way like using like the first delay as a proxy for all the other noise is some way to target a memory in that. Okay, so let's see the results. So here again, similar to what you saw, that it just maybe a better way. Participants just choose with the mouse the color that they remember it to be, and let's say that was the true color, that was the color that they reported, and now the angles represent the amount of error, right? Angle 0, as we saw before, means that the report was real. It's the same, identical to the display color, and higher, larger angle means larger error. And now, let's look at the results. Here, just plot the different delays. Okay? And here, just the average error. Okay? thing that is interesting, because also distracted, or also this long arrow is also, actually these long arrows is what you might predict if, according to your intuition. If you just have an item and the only thing that happens is just disappears from your memory, then you would predict the participant to report some random error.
Well, in the original experiment, in this experiment that works, because in the original experiment, there you have the possibility of confusing which color was in which place. Here you have a single stimulus, so I think that the memory of the stimulus stays, and you don't have as exact of a representation. So here, I mean, this makes sense to me.
Okay.
Yeah.
So it's not. So I'm gonna show you that at least that what probably happens with maintenance is the two processes. One is that in some cases participants just forget a color. I don't know, maybe they just remember what happened to a boyfriend or girlfriend, and they just forgot what they saw. Or so there are two processes. One is just disappearance, sudden death, that people call it, of the memory, and the other thing is just precision. Well, things become less and less precise, and I will try to show you talk to you about neural processes that might be related to this precision. But from here, the nice thing that you can clearly see that most of the errors are really small, but there are few errors very big. That these errors might represent catastrophic events in memory, or just sudden death, sudden disappearance. And we did that for all participants from the different delays. That's just one example to show you. And just from this example, we can see that we have a slightly more random errors, but also the small errors also something happens. And now let's look at the way to try to quantify, to separate these random errors from this from this precision errors. What we can do is just do this histogram that we can see. Again, zero are exactly these kinds of trials. Participants reported exactly what they saw, and the really big errors, we can see that here a little bit, and here we can see the more. Here we have big errors, so we can just do the histogram of the errors. Here is the amount of trials. It's all per participant, per delay. Here is the amount of the frequency or the probability, or the number of trials, and in x-axis is the amount of error. And now what we can do, we can do a mixture modeling to try to fit to this data. That's what you actually see here in this. It's just a fit. We fit a Gaussian distribution, a cyclic Gaussian distribution around zero, represent what's happening when, like in these small errors, when you have some representation of the memory, but also we have this random uniform distribution that represents all these very random errors. Okay, so we have this mixture, two distributions that we try to fit to our data, and by data fitting tells us what's the probability, or what's the number of trials that could be attributed to this uniform component. You can see here there is slightly here we can see an increase in the uniform distribution, and again, the width of this distribution tells us something about how precise subjects remember the items of these presented before. Okay, that makes sense? It's exactly talks about this distinction between sudden death or just precision. But the interesting thing is that now we have this delay. So what we can see, and the interesting thing is not to talk about the actual values, but to see what's happening when you forget, when the delay is increased, because then you really target maintenance or memory processes. So first, let's look at the random errors. We can see, again, increase in the random errors means that these random errors or that might be related to a sudden disappearance rate just doesn't really change with time. Uh, but what we do see when we talk about like the precision, uh, what we do see is that there are also decrease in precision, like or increase in the variance in the standard deviation with time. So it's not only that there is a chance that items just disappear from memory, also the items that we do, the representation that stay in memory, become less and less precise with time.
Could you explain why is the random error distribution Gaussian?
No, the random is uniform.
Oh, the random is that line at the bottom there?
Yes.
Ah,
Yeah,
okay, gotcha.
yeah. The
Okay.
random is just is uniform, not also
Okay.
from the by definition. It just yeah, maybe the I should be clear. Okay, so that's the two. When we split the data, we can see that both things happen. It's not only the disappearance of memory, also the precision of memory degrades with time. But here we can see, at least in the precision, that at the beginning the rate of forgetting is much steeper than afterwards. So there is much less linear with time. It's much it's sublinear, what we can call, and we can talk about that later, how we can maybe explain this kind of dynamics. Okay? So what we can take out of that, just if we compare it to the slot model, that items just that there is slot for an item, that items in memory don't just suddenly die. There is something about the precision of memory, and precision degrades with time. We said we're going to do a break every 45 minutes. That's how we do it. And what's the time now?
If it's good for you to make a break now, we'll make a break now.
Let's wait 5 minutes more and then we'll do the break. Just because the next experiment is really similar to that, and I just want to show you that we get these behaviors from in a completely different task. So that's just called color. Let's see a different task when you try to remember location. Okay? Item first subject fixate here. They see a circle, and then they see a dot in a random location on the ring here, and then this dot disappear. All the time they need to fixate in the middle. So here along the delay, again variable delay, same times as I showed you before, the same duration as I showed you before. They need to maintain this location, and then after the delay, fixation disappears, and they have to make eye movements toward their remembered location. And again, the interesting comparison: what's happening here? What's happening when the delay increases, when you try to maintain it on for longer and longer? And so that's just that's the different points that we use, and that includes like the different endpoints of the actual saccade. And we can see that there is some noise here. What we can quantify is one. We talk about the angular noise here, what's the direction of error, and about the amplitude of error. Okay, so what was the amplitude difference? And so here we can just plot it. Here 0 is that the direction of the saccade was really the same direction as the display point, and gain 1, it means that the amplitude wasn't exactly as before, as expected, as the display. And now the interesting thing is to compare here. There is another interesting finding that we still try to make sense out of that. That longer, like overshoots of the saccades are more precise in that direction. But leave that aside. What we can do is now take the variance here, like that tells us something about the precision of memory of the amplitude, memory of the amplitude, and the variance here as a proxy for the precision of the direction of the point that you have to גובה. היוניפורמית, ואז השטח הזה אומר לנו כמה אחוזים מהטריילים אנחנו יכולים להתאים לפה, שזה בסביבות 4% עד 10%.
אמרת כן עולה עם הזמן.
כן, בכל מקרה זה עולה.
אבל ליניארי.
פה זה יותר ליניארי ופה זה פחות ליניארי.
כמו שפה זה פונקציה ליניארית של הזמן, ככל שעובר זמן פחות זוכרים.
בכל מקרה, ככל שעובר זמן,
כן,
אנחנו
אבל
יותר
כאילו
זוכרים.
ברמה.
אז פה פשוט הקשר בין כמות הזמן לגידול בסלייד הוא ליניארי, הוא קבוע, ופה זה קשר אחר שיש איזושהי סוג של תפאורה. זוכרתם מאיזה קורס אחר, לא?
שניים, תגיד לך מה שאמרת.
עברת בעצם?
לא, אבל סיימתי איתי פשוט. כאילו, איתי לא משנה.
בטח זה קשה, לא? מאיזה רקע הגעת? איפה ביולוגיה? כן, אבל...
קשוח.
כן.
כן, אבל...
בסדר. קשוח אבל זה היה פרסומת לאוניברסיטה, לא קשה, אבל הכי טוב, כזה.
משהו כזה.
אז זה מתאים מאוד לפה, אני יותר.
למה?
juegos que ahora sí.
פשוט רק איפה אתה מעדיף אותו יותר?
חבר גרפיקום ככה, צריך למדתי ללמוד
ספוילר? אני למדתי סטארט-אפ 4. יכול להיות שתכניסו מעולה תביא זה כאילו עשיתי מ-0 עד 6
איפה, אבל...
כאילו עשיתי מ-0 עד 4 ואז מ-0 עד 6
זהו, אפשר להוסיף? הם לא ידעו איתי.
הוא רק יצא פעם אחת, הם רק יצאו פעם אחת, אני מסתכל עם זה.
פעם אחת, טוב, אז יאללה.
אבל זה בסעיף האחרון? אבל רק כתוב את זה בסעיף. את לא מראה בכלל. לא, זה יפה, לא? זה בהחלט הפרופורציה. לא, אבל זה הפרופורציה מבחינת ה-CIE. לא, סתם, זה יפה כזה CIE. כן, כן, כן. תראי, הצ'ופצ'יק הגדול, סתם, רפלקסי, מאוד מאוד גדולה. תראי, זה לא כזה, זה היה לי בהתחלה. לא כזה גדל, תחילת בן.
טוב. אז נמשיך, ראינו את הניסוי של התנועות עיניים. Sorry, we're going to continue. We saw just mean that I'm using it for 2 years enough to be used to Hebrew again. We saw in 2 different experiments, eye movement and the color experiment, that we can also see forgetting slope with time, degradation, and it seems to be sublinear in some sense. So the next step is to talk about, well, what might lead to, or what the neural mechanism that might be related to this phenomena. And traditionally in cognitive psychology, people have debated in the realm of verbal memory. Let's say people have debated if it's interference or just decay, and it's still a debated issue over there. Here I want to talk about a slightly different way to talk about that, is the accumulation of noise in bandpass transform. Okay, I guess all of you did already studied neural networks. In the middle, with Yoram, Pura? Jonathan.
We did this morning.
The bandpass transform. Great. This one, the PNS study? No. Just about the idea that bandpass transform might be a way to represent information no longer present in the environment. Did you talk about that? So I'll just say it in a few words. It means that the idea is that you have neurons that represent similar So that's one of the basic ideas about connecting persistent activity of neurons in the brain to maintenance of information no longer present. And now, so now there is also a new Nature Neuroscience paper that actually studied real neurons in the frontal cortex of the brain, and the conclusion that what they see really support this prediction. And now what Yoram Borak and Ina Fiat published not long ago, they tried to quantify this kind of behavior and look at the jitter. Now, during the delay, the stimuli disappear. We have a hill of activity, and this hill, because of neural noise, this hill can move around. Because of neural noise, it just moves in what people call random walk or diffusion process. All around, here is the delay, just it starts here, but it's going to end after the delay in slightly different rotation because of this random walk. And what Yoram Borak and Ina Fiat, like in a theoretical paper, they try to quantify what would be, in this scenario, what would be the variance across drugs that you might expect, what would be the error or the variance that you might expect with relation to time in this kind. And for us, it was really, I was really happy to tackle, to see this paper, and I was even more happy to find out that Yoram also came back to Jerusalem, so we continue to talk about this idea. But it's a nice way to do this jump from neural processes to performance, because we had like this cool way to talk about the precision of report, and so that's the idea that I want to talk about. One neat way to demonstrate why would we expect to see increased variance with time is
Just, can you go back to the previous slide for a second? So I understand the blue and the red, but I'm not sure I understand the yellow. In other words,
here the yellow.
yeah, in other words, so if all the neurons that create this particular representation are exciting each other, inhibiting everything else, so what does the yellow represent? Isn't it like a binary thing?
I think the neurons it's about firing rate. It's not a binary neuron. It's not kind of like like the classic neural networks of either fire or not. Here you talk about maybe it's firing rate. Each neuron has like a more graded chance of being of like the spiking frequency, what we say, and the red ones are the neurons that fire more.
So there's some probability of exciting neurons that aren't representing a particular pattern.
Yes, it's the neurons at the edge. They get some of the excitation, but they don't fire as fast as the neuron in the middle. Okay. And then if you try to encode what's happening, you just like the encoding is just taking the middle, so the decoding of that, let's say, is just taking the middle of this distribution of this field. But I don't want to get into the neural network, so I take that as my model, and I try to see. Here is just a way to show again. So let's say now we just take the middle of the hill of activity, and we know that the middle of the hill of activity with time it has like this random walk or diffusion process. It just randomly can go clockwise or anti-clockwise, and when this happens in a lot of trials, we're going to show you that. Maybe it's because of the split screen. Okay, one second, let's try it. Okay, one second. So, well, the idea is like that. Okay, when let's let's say the bump starts here in every trial, and each trace is just a different trial. We have this random walk across time, but what we can see is that if we just talk about the variance across trials, so at the beginning the variance is relatively low, and it increases with time. Okay, just a neat way to show that. And
Can you just say what we're seeing exactly?
yeah, it's just a simulation. What I
Sure,
did
no, but
say is
what
just
the
a simulation.
simulation is.
Let's say that was the color or the location of the target item, and I just plot diffusion model, like a random walk that can, in every millisecond, it can just go either upwards or downwards, or clockwise or anti-clockwise. And I just simulate that and run a lot of plots for this one trial that just has this random
So
walk.
the idea is this is supposed to simulate the delay.
Yes, what's happening with the delay. With the delay, there is this neural noise in this bump attractor, and can just move randomly. And from this, we can predict that what really happened was it's just a neat way to demonstrate that we would expect to have the variance across trials to increase with time, because we start at zero, we start at the display point, and there is this noise in the delay time. Uh, uh, so from here, what NCF just they try to analyze that, and they say, well, that in this single random walk, the variance should increase linearly with time. But what we actually see that what we see is that it's sublinear. It's not linear with time. So what might happen? What might cause this being sublinear with time? What I want to suggest here, and I have some data to show that but it's still very preliminary. The idea is like that. That now, instead of just random walk, we have this bounded diffusion model, bounded random walk. You have from like the color or the location that you saw, you can still have this random walk or noise, but it is bounded by borders that might be related to categories. Let's say if you remember color, at the beginning you have like a very sensory information of our more exact information about the exact color, but and there is noise that just changes, but it cannot move from red to green. There are some bounds, or let's say in the location, first you have a very precise information about the location, and it starts accumulating some noise, but you cannot really move between categories. If it started at the top right, you wouldn't make an eye movement to the bottom left. And according to this idea, at least, so now in this browser that just exit this border, they wouldn't exit anymore. They just keep in this channel. And what's happening is at the beginning there is a big increase in the variance, but afterwards the increase in the variance because bound in categories and people start categories starting to be more influences, the variance stops increasing with time. And when we use, I don't have it here, not in this presentation, but when we try to simulate this and to have, and it seems to fit to the data pretty well. When we inject this category or bounded models to the diffusion, we can see that it quantifies pretty well what we see in our data. Now, just move to a different. Okay, so that's.
Don't you need, in order to look at this kind of, compare your data to simulations, don't you need like really a huge number of delays?
So I have, in this case, 6 different delays, and now we do that with in longer delays to try to distinguish better. Yeah, but it depends on the other process that you want to compare. It's clear even in our selection of delays, it's clear, and I think we can show it pretty clearly, but it's not linear. It's not a simple random something sublinate, and we can show that it fits better here and here. But in order to distinguish between a few other more complex models, then we need more delays, and that's what we do now. Okay. Yes.
I wonder if after a certain amount of time, so if you have that death rate as you increase the interval between the stimulus and the probe. So I wonder if at a certain point you actually don't have any representation of the original stimulus at all. You're not even trying to represent the original stimulus, you're only trying to represent the category. So you have a category called blue, and at that point you're just picking randomly anywhere in blue space. Or an alternative might be that you actually you do have a category representation, but the category is represented by a characteristic color. Like in your brain you have representation of, let's say, 12 different colors, that perceptually you have more, but in terms of memory, if someone asks you to think of blue, you have a particular representation of blue and you choose that one. I think that if you compare different trials with the same color and see what people did, that might be interesting to see if people sort of tended towards picking the same
Yeah.
choice.
So I try to analyze this kind of, to talk about this kind of question. Let's say here, right, in the color, I saw this like gaps in the report. Okay, so what I did is, and I know that the display I determined the display. So and I said, well, if there is some category issue that people just use the typical color, I should expect the report cycle to be less uniformly distributed than the display. Exactly because relates to the question that you so then there are ways I try to quantify how different the display from uniform, and to see if the reports are less uniformly distributed than the display. And what I found that indeed the other way that we do, now we use this task, but with clockwise like slicks on a bicycle. That's called bars here that you have that should encourage people to use categories instead of just remembering the location to remember items. You use the clock position of that. So I try to look at these questions of categories and all that, but at least that's that's one way to talk about it. At least in my mechanism should work, but I'm sure that there is this balance between categories, that category memory is more pronounced in longer delay, and more sensory, more precise memory is more pronounced in short delay. Focus it. Still I talk here. Yep. Because I don't have enough time. Okay. So now the next question is, well, we talked a little bit about the mechanism, we now see another idea about the mechanism, and we saw that there is forgetting of how precise to remember memory, and now a few more questions that we studied relate to, well, what influence this forgetting rate that we see. Is it something determined? Any object that we don't see, we're going to forget it at the same rate, or try to find out what factors really determine how fast we forget. So we have three factors. Yes. But
My question is about the categories are. How do you define the categories? They require language, the visual categories. What are called categories?
I don't want to bound myself. It doesn't have to be verbal categories. It might be something more visually. It's just.
You can say that there is categories all the way. Even when you in the beginning you are doing well, you also have categories. Can you say that? So what distinguishes this?
I can say that, but I think at least my data shows that at the beginning there is the precision of recall really deteriorates with time. As I see, categories are something that are more stable across time because you can rehearse them in somehow. So as I see, at the beginning at least, the information is more sensory and less categorical, and afterwards somehow more categorical. But
It's not well defined. So how can you say what is category itself?
It's just a suggestion. It's
Okay.
not well defined. It's let's say in this case, I would say categories are bound on some analog space. That might be my assumption here. But it's just ideas. Nothing is really published about that, and I still need to think about that. But just I think that's how memory works, and I still trying to find out how to show that and what terms to use. But maybe the best term is to say category is bound on the. One second. Nobody cares. Okay, so let's talk about like three other ways, three factors that might influence how we forget items. One is the number of items in memory. I want to show you now. slightly different task, but it's all the same. Like delay, like analog kind of responding. Here in this task, participants just see different number of color bars in random orientation. And again, there is a variable delay, and afterwards they see a bar in one of the colors in random orientation, and they use this die, it's like a volume die, and they adjust the orientation here to match the orientation of the bar in the same color that they remember, and again the angle represents the error. And here again, what we can plot is just a distribution, zero errors, and what we kindly see here, here we place the delays, shorter delays of 3 seconds. When there is one item we can see a small effect of the delay, and when there were 6 items was presented. Again, only one item was probed, just determine the number of items that you try to remember along the delay. We can see a decrease, a faster decrease or faster forgetting rate. We can just quantify here just the average error we take for one item and 6 items. We can see that the slope of forgetting is much steeper for 6 items compared to 1, and it's the same is true also for 2 and 4. So what we can say that more items in memory leads to faster forgetting, faster degradation slope. And if we compare it to the slope model, at least the slope idea is just that you have items that are just represented in memory in independent slopes without any interaction. And here there is clearly interaction in memory, in maintenance. Clearly items in memory somehow compete on maintenance resources. I don't want to, I still don't know exactly what kind of resources, but it's really some maintenance resources. Right? When you try to remember 6 items, you remember them, you forget them slower than 1 item. But to get into that, maybe because you are in health. Yes. So because it's interesting way. It's a bit harder to explain this using a simple bump or interface. And it's the case that there is a neat way to explain what's happening, and I think I like the concept. The concept here, we just submitted it now for publication. The concept here is that memory, you might look at memory as a communication channel. Right? Like in engineering, the first thing that you study in communication channels is that you have a signal, you encode it to some noisy channel, then the signal degrades with distance in this noisy channel. You have a decoder at the end of the channel, and you try to predict or estimate what was the signal that was injected to the noisy channel. And Shannon, like the founder of information theory, he said that, well, if given the channel noise here, you can find out what's the rate of information transfer that you can transfer across the channel. Okay? So that's communication channel, communication system engineering. Let's look at the memory analog. We stay with the encoder and decoder. Here the stimuli, just visual stimuli. They get encoded into a noisy memory. The noisy memory is represented by a number of linear factors, like we just saw, that the noise over there accumulates linearly with time. And now the noise accumulates with time rather than the distance in the communication channel, and we try to decode what was the signal injected to this channel. And what we theory and tweak it for our purpose. And, and what we've done, try to give the time that relates to the amount of noise in the system and the number of items or the number of the information that we want to transmit, try to predict what would be the amount of error. If you want, I can send you the graph about how the trick of how to move it with you. It's a bit complicated theoretically, but it is possible and it's valid. And when we do that, our data about 1 item, 2 items, 4 items, 6 items, that's just the root mean square error, or just the mean square error, and we can see only 2 parameters that we have to fit, just the number of independent ring factor here and the noise rate. Here we have pretty good fit to our data. So I just wanted to present, and I think I like the concept, using information theory tools that were developed to try to quantify information transmission in real communication channels, and seeing if it applies also to our method.
But is there an equation that gives you that graph? Is that?
Yes.
Oh,
And the development.
You have the equation, or is that like?
If you want, there is a limited amount of time that I can spend here. If you are interested, I can send you the draft. Okay? Yes, but it's equation, so okay. So we saw that more items in memory can influence forgetting. More items in memory or forget them faster. Here, I want to talk about retrospective attention. Let's see what retrospective attention is. Okay, let's do together the experiment. Try to look here. Try to remember this color bar, the colors and the orientation. Okay. Now there is a delay. Now I'm going to tell you that we're probably going to ask you about the blue bar. Now there is a variable delay. Now the blue bar is presented, and you have a dial. Someone remembers the orientation of the blue bar? It's a bit longer than that. Yeah, or something like that. Okay? I'm not sure that it was the same color. The idea is like that, right? You see items, they disappear. You wait 1 second afterwards to live, let's say, all the what people call it iconic memory and all that. You wait 1 second, and then you give a cue that a participant should use, because the cue is predicted in 70% of the time we really ask about the cue item. So subjects are encouraged to use the cue, and the cue tells them on which item they will probably be active afterwards. And here we play with the delay again. And now we can see how this cue influence the forgetting rate here. Let's see the results. So again, that's time. 0 here is the time of the cue. Here was the stimuli, like before. And in blue, we can see trials in which we actually probe the item that we cued. In red, we can see that in 30% of the time that the cue was presented, we probe an item that wasn't cued, like the green, yellow, or red here. And in green, we can see what's happening when in the same delays without any cue. So what we can see that also after the display, when you only have like memory representation and you have a cue, you can direct your attention. You can call it attention, or there are many names for that. Or you can move memory resources towards a specific item in memory. And once you do that, the forgetting slope is much better than without any cue, and even better than the forgetting slope of the other items in memory. And what we can actually do is overlay the slopes that we found in the previous experiment without any cue and with memory. So what we can get out of that the directing memory resources or retrospective attention. It's called retrospective because the actual presentation was acquired long before its use. So retrospective attention can influence forgetting. Okay? The last thing here in this part that I want to talk is again something that we only now we try to that's very recent result. One of my students from here is the question is like that. Is it the case that if you remember something better, if you encode it better into memory or working memory, does it mean that you're gonna forget it slower? And I think that's really critical question that nobody asked before for some reason. So what we do, probably because people it was really hard to find forgetting slope in the sense of few seconds, in this realm of few seconds. And our tasks are more analog, really reveal this forgetting slope. So what we did here is just to have again 4 items, 4 oriented bars. One of the bars, a random one, has 300 milliseconds more than all the rest. So you might say that it is better encoded than all the rest. Then there is a variable delay, and they need to report the orientation of the bar. And the interesting comparison now is to see what's the forgetting slope, how much the delay is related to how much time you have to encode an item. And what we do see is that items that are better encoded, you also forget them more slowly. Items that are worse, have worse encoding or they have less time to be encoded, they also you forget them also fast. Yes.
Why do you assume that forgetting is linear?
I'm not assuming.
Because
We showed that it's not linear.
probably exponential or something like that.
Yeah, we actually when we have more data, we show that it's not. But here we just use 2 delays. Maybe the best. It's just a MATLAB graph that is doing that. I don't assume that it's linear. But what I can say is that the slope here is larger than the slope here.
But this might be the same exponential decay curve, but one of them started at a higher initial point, and for that reason the average slope would be higher, even though the characteristic decay time would be exactly the same.
Yes, but we still need, but the difference here in the precision is much smaller than here. I agree that maybe if you assume that it's not linear, the decay slope, it might not, the difference here might be explained by the difference here, but we will look at that. I just it's very preliminary results. Okay, so I wonder how long, what's the time now?
It's almost 3, so we can, in a few couple of minutes, we can take a break and then come back.
And then come back for the last section that is completely, so let's just summarize what we have here and before the next time, and we're going to come out for the third part. Hope it's not too much. Third part is actually with a little bit practical implication. So what we can learn that objects do not just disappear from memory, precision degrades with time, and the deterioration rate decreases with time. At the beginning, the decrease is steeper than afterwards. We also showed that more items in memory are forgotten faster. So sometimes somehow items compete on the same maintenance resources, forgetting
לא עשית לו מחסום?
של...
אתה רוצה תתני להריץ את זה? אין בעיה. נראה לי שצריך כי אם יש 5
אני
אחד
עשיתי משהו
ואחד...
שאני אף פעם לא עושה. כתבתי 20 שורות קוד, ולא עבדתי כל רגע.
נראה אם יש לך
we're strongly encouraged to cancel the last class because of this content rainy days. What can we do? We cancel the last class, and that leaves us 3 more classes. And what we're going to do in the next 3 classes, we're going to talk about numbers, the perception of numbers, the cognition of numbers, and you know, the relationship between quantities and expressions of quantity and things of that kind. So what we're going to do, and next time we're going to talk about phenomena that pertain to Weber's law, which most of you have discussed at some point, and those who haven't will teach you a little bit about that. And we'll start off this time. We'll start off with experimental results, which show you facts, and then we'll discuss the significance of those results in several ways. What we will ask you to read for next week is a very short and sweet article. It's 3 pages. Doesn't make it short or anything, but it's shorter than previously, with less words, at least. And by Stanislas Dehaene, which gives you like a short summary of some experimental results mostly for monkeys in numbers. So we're going to put it up, and this is going to be the section, the new section, the section of numerosity, and it's also going to be the last one. Next class, we're going to talk about these results. We will enrich them with some results that come from humans. And the week afterwards, maybe a week before the end of this class, we're going to give you a homework assignment about numbers, numerosity, and perception of these things. And then we will give you a final, we have to still negotiate the exact time, but we'll give you a final takeaway.
Okay. So in the last part, I'm going to talk about more real life situations that requires working in real life. In real life, we hardly remember the orientation of a ball or the exact color. We touched that a little bit about the position with the eye movement, but that's just an example of eye tracking experiment that have just like a schema of a real room that subjects had to, in this case, they try to prepare tea, and it just here they prepare tea, but that's in the UK, and in America they did something similar for sandwiches. And what we can see here is just the endpoints of very large orienting movements. It means moves of the eyes and the head towards objects that were like more than 90 degrees from the center of gaze. It means that subjects here use some memory presentation of these objects, because 90 degrees is much more than the field of view that we have. So it just to show that we do use object location information in real life scenarios. So the way that we try to study this object location scenario is object location memory is this way. Like subjects were presented with 3 fractals, 1 or 3 fractals in random location on the screen. We use fractals in order to hamper any verbal kind of coding and to probe visual object memory, because it's really hard, once you see these fractals, it's really hard to give name to them. And then we use variable delay, again, because we are interested in what's happening when you forget items. And then then 2 objects are presented. One was really presented before the other one is a fault. Different files, and subjects are required to touch the fractal that they remember to be, and it's a touch screen, so they just move it to the location that they remember it to be. So again, there is some analog report here in the location, which is like the resolution is the resolution in pixel-wise resolution. And we're gonna see it's really easy task to perform. People what we can get out of it is one, is memory of how well you remember the identity of the object, just analyzing its subject, subject touch this item, the, the correct target or the foil, and we can also have some memory of localization precision, or how well they remember its location. And let's see if it works. It's just a cool way. Not sure, but in this. Anyway, let's keep moving. So first we can just test if subject remember clicked on the correct item or not. Here is the delay, 1 to 4 seconds. Here is just the proportion of correct. 1 factor, 3 factors, and we can see that there is some forgetting flows in 3 factor and 1 factor, but it doesn't, there isn't any interaction between the number of items and the forgetting flow. To remember a bit less precisely the identity of the factor after 4 seconds, but it's the same for 1 and 3 factors. Next, we can just analyze the localization precision, right? How, let's say, subject is, they put the factor here, and in green you can see the original location of the correct factor, and in red it's the original location of the other factors in the memory array. First, we just take the distance between the reported location of the factor and the true original location of the factor, and the error we just quantified instead of pixels or centimeters, it's just in degrees of visual angle. That's how usually in visual neuroscience we quantify the amount of error. And here again is the delay. We can see that the delay will influence the precision of report of 1 factor, but when you localize 3 factors, the forgetting flow is much faster than in case of 1 factor. And just remember, from the oriented bars, we saw the same thing. More items, like the arrow, increases faster than in 1 item. But here we have a neat way to try to see why in 3 factors the precision, like localization precision, deteriorates faster. Let's see why. In many cases, what we see is trials like that. Participants really localize the factor fairly precisely near the location of one of the non-target items in memory. They just remember well which item was presented, but they put it next to other items in memory. We call it swap errors. They remember well. Again, all localization data is just, we do it just on tracking with that the participants identify correctly the items. So in such cases, participants identify correctly the item, but just put it next to the original location of one of the other items. And when we count the number of cases that these swap errors happen, we can see increase in time. Like, that's just a percentage of objects or trials that it happens. So when time goes by, you have more and more swap errors. Now the interesting thing is to see if these swap errors that could happen only in the case of 3 factors, because when you have 1 factor you have only 1 item. If these errors can account for what we see here, this increased forgetting flow in 3 factors. So our way to try to see that, we call it the nearest item control. So in that case, let's say participant just localize the factor near the location of one of the other factors, and because of that, now we take here into account a very long error, a very large error. But he actually tried to localize this factor near this location. So what we can do is just take the minimum distance between the fractals and any one of the original locations, regardless of the identity or the true identity of the fractal. So when we take this nearest item control, or the minimal first, if it's just chance on the screen, I'm gonna show you next. It's not chance, but if it's just chance, you wouldn't expect to see any effect of delay, right? Because if it's all chance, you have this variable. It, the delay doesn't really matter. What I'm not presenting it here, but we did that in the paper, in the published paper. What we can actually take is this distance, the real distances, and just randomize the angle. Say, well, if that was the error, regardless of what the original location of the other item, let's just do this bootstrapping. Take all the different locations that might have happened if assuming no bias towards the original location of other items. And when we do that, we still see that there are much more swap errors that you might expect just from chance. And here, chance is a bit more complicated. It's not, we are not assuming a random location on the screen, assuming the same type, the same distance of error, just with random angle. I don't want to get into the details, but we were able to show that this phenomena it couldn't be attributed to chance at all. There is some bias to report the location of the other item in memory. Okay? And the way that we did it, we just took the actual distances of the subjects and just randomized the angle, and we show that if there is a bias towards the location of the real. But what is interesting here is that the increased forgetting slope in 3 items is probably attributed to these swap errors. So maybe what's happening in time, you have some deterioration in the precision, in just the localization precision we can see here and here. And we saw before that there is some forgetting slope of the identity of the object, but it's also the crucial critical process that happens here in the forgetting is just that it's hard to remember what was where, to bind the correct identity to the correct location. You have fairly precise memory of all the locations. You also have fairly precise memory of the identities, but this association of identity to location seems to be more fragile, at least across time. And we're going to see more data I hope to convince you that it's a critical process, this object location binding. And we also have some clue about the brain processes, or at least the brain regions involved in that. Okay, so it's not a simple memory degradation, but we do we see a lot of swap errors. And leave that. And how we look at it, again, it might be the case that we have a memory of the object, of the identity of the object, we have a memory of the location, and there is this binding process that bind or associate the correct fractal to the correct location, that this binding process seems to be also fragile with time. You forget this association that leads to this increased forgetting when you have more items in memory. And now we know that the hippocampus is involved in making associations, at least in long-term memory, in episodic memory, right? If I try to remember, like, if you ask someone about episodic memory, which people someone met in the pub 2 days ago, then probably what's happening is that the representation of the pub is retrieved from memory, and the representation of the faces or the people that he met in memory, in long-term memory, people call that a relational hypothesis about the hippocampus. And if you talk about brain processes, it might be the case that the hippocampus just bind or associate together representations that reside in actual, in the cortex. So what we wanted to see if the hippocampus, if it is involved the same thing here in our task, that again the delays are just 1 and 4 seconds. It's not classical episodic memory or long-term memory. Usually people just distinguish these two processes. So one question is to see if maybe the hippocampus is somehow related to here, and our hypothesis that it might be most strongly related to this binding process. But at least according to that HM, well-known patient in neuropsychology, that is the hippocampus, the bilateral hippocampus was dissected or was removed, and he had like long-term memory deficits, and but not short-term memory deficits. So using HM here and other study, people have made this distinction between long-term memory and short-term memory. So at least according to this multi-store, the hypothesis that you have different processes for long-term and different processes for short-term, based on this hypothesis, would predict that such patient would be fine in this kind of task. So because the delays are very short, just 1 and 4 seconds. So what we did, that's part of the thing that I did in my postdoc. Over there, I was working with a lot of neurologists, so we had good access to really interesting patients. So this group of patients, they have a condition that is called voltage-gated potassium channel antibody encephalitis. Here we can see just the flare scan of in the acute stage after the illness. We can see a abnormal signal in the medial temporal lobe of all of them. So we tested 7 of these patients that show amnesic properties as the classic hippocampal patient. But this group is, like, this condition was only recognized not long ago, and the nice thing that they actually respond to treatment. So after mostly they give them steroids, and it helps this the inflammation that they have here in the middle temporal lobe, and afterwards they behave almost as normal. And now people study, and probably this condition, this encephalitis, it's related to enhanced level of antibodies that attach to specific proteins that is expressed very restrictively in the hippocampus, and also post-mortem studies of such patients, they show neural loss especially in the hippocampus and a little bit in the amygdala. So it might be the most clean group of patients, of hippocampal patients that people have studied, and that's why I guess it was published in very respectful journal of neurology.
How exactly do you localize the hippocampus? You just identify visually?
So here it's very easy to localize the medial temporal lobe, like it's the whole structures that include the hippocampus. Just from this scan, we cannot really say that it affects only the hippocampus because the resolutions are not as good. Now we test this, we scan these patients with 7 Tesla MRI, that it might be easier to say that, even to quantify how much degradation they have in how much atrophy they have in the hippocampus. Right now,
Even if you do have higher resolution, you still want to delineate the hippocampus. And the question is, what principles guide you when you delineate it? It's just
so for now,
you have to,
but
without some localizing, some other localizing tool. You only have
research center, and this the people that study dementia, they have like really they have tools for doing that automatically. Also.
That still doesn't make it necessarily correct. It's just I'm asking because I don't know that they published it, but there are cytoarchitectonic maps of the hippocampus. I'm not sure that they're published. The person who did it is very slow. But in Yiddish, they have cytoarchitectonic maps of the hippocampus. In fact, they can parse it into different parts of the hippocampus.
Yeah.
And otherwise, it's very, even though it's a clear structure and you can see it, it's very difficult to establish the exact areas, especially if you're looking at pathologies.
Yeah.
Inflammatory processes make
Yeah, here it's
make things very blurry.
yeah, that's why here we say actually medial temporal lobe, because we cannot really say that it's exactly the hippocampus. The reason that we try to say that it's the hippocampus because of postmortem studies, then it's easier.
But you see, if you start overlaying postmortem maps on these things, you start facing the problem of inter-subject variability.
Yeah. But if you have some previous data that take the same kind of condition, the same encephalitis in patients, and you show that over there it's exclusively the brain loss, the neural loss is exclusively in the hippocampus and amygdala, then it suggests that the deficits here are related to hippocampus, but I cannot be sure. You are correct. But we're going to show. But I use the automatic criteria that they have, and we also have data on that. And at least in the dementia research, the conversion is okay to use. It's automatic, but I can't be sure that it's really correct. Anyway, so we use this kind of patients, and we can say that it's the brain lesion is restricted to medial temporal lobe. Just to compare to other hippocampal patients, most of it are from anoxia, and it's probably the other deficits that people have studied and say that the hippocampus are much less focused.
Well, that makes sense. If it's something that targets the hippocampus and nothing else, I think you're
Yeah.
right.
Because of it targets like a specific proteins that are more expressed in the hippocampus. Yeah.
So it really promises to be more selective than Oxia or...
Yes, it's better than than previous studies, but it's not the best. It's always a problem when using patients. And each patient is completely different story. But let's see, the data is pretty clear there. So here we use the same task, and now it's just the identification, how well they remember they click the correct item at the beginning. And we can see that these patients were within the normal range in identifying the correct items, in remembering which items were presented. When we look at the localization precision, again, just the distance between the location of the fractal and its true location, they were also, when one item was presented, they were fine, like within the normal range in this localization, but they were impaired in localization precision when three items were presented. Again, only one, after the display, they had, in all cases, they had to just report the location of one item, but the difference is in the number of items that were presented at the beginning, initially. So when three items were presented, the distance, the location error was much much larger than in the controls. Again, healthy elderly controls are matched in their age and education levels and all that. So now the question is, what types of error will relate to this impairment, and when we count the number of...
Make an anatomical point again.
Yes.
Here, since you see, I mean, this is very nice, you see a split in the errors that those the patients are making. So they're making selective errors.
Yeah.
What you would have hoped for
try to do postdocs now,